Today's lesson, we're going to look at how to sketch graphs for rates of reaction and how they can be influenced. So let us have a look at these two scenarios. There. So interpreting graphs. Before we even start, just remember that the rate of reaction will be equivalent to the gradient of a graph because it's always per unit time here. So suppose you have calcium carbonate plus hydrochloric acid. What does it make? We've been over this before. It makes calcium chloride plus water plus CO2, carbon dioxide. So we could measure the mass or the volume of CO2 formed. So let's put volume here. We could connect a gas syringe, and we could put time here in seconds. A graph would look like this. Now, why did I make it a curve, not a straight line? You need to know this. So at the beginning of reaction and at the end of reaction, we need to consider what's happening. At the beginning of the reaction, we have the most reactant particles. We have the highest concentration of acid and the highest, I'm going to abbreviate this now, frequency of successful collisions as a result. Okay, remember FOSC, frequency of successful collisions. Now, as the reaction proceeds, the concentration of acid decreases and eventually runs out, provided that the calcium carbonate is in excess. You could also reverse the argument. So if the acid is in excess, then the calcium carbonate would run out. Either way, the reactant particles would decrease. So eventually, we need to write down that over time, the reactant particles are reduced, / the acid concentration decreases. So the frequency of successful collision falls, decreases, until eventually a reactant runs out. It's called a limiting reactant. So the rate decreases to 0 because there's no more successful collisions. So that is the principle of explaining the graph. It can be worked up to 3 marks because you have to explain why this is the steepest gradient, which is the fastest rate. That's the fastest rate there. And then as the reaction proceeds, one of the reactants is running out, or they're both running out, and the frequency of successful collisions decreases. Eventually, one runs out and the rate falls to 0, so the graph flattens. Okay? Next, you could consider measuring the loss of reactants per unit time. So, for example, the decrease in acid concentration can be measured with pH or with conductivity. So then the graph will fall like this. It'll be the same explanation though. So you could put time here again. And here you could simply put, well, pH wouldn't be a good one because pH would actually increase, not decrease. So for concentration of acid, you could put conductivity. Because the conductivity will go down because the H+ ions will decrease as the acid concentration decreases until it can no longer conduct electricity. Or you could just measure the loss in mass of reactant. At the beginning, you would lose the most CO2, then it'll be slower and eventually stop. So let's save this. And let's look at the next bit. The next bit is the effects, these 3 effects. So I'm going to try and squeeze them on one sheet of paper so we can see all of them. To make it a little bit smaller. So there. So I've actually repeated collision theory here for you. So surface area, use everything the same, but change the marble chips to be smaller. So they have a higher frequency of successful collisions. So if I draw my original curve in black, well, I can't. Ah, here we go. If I start by drawing a black curve for each one. So we're just considering the calcium carbonate reaction and measuring how much CO2 is produced. Let me just change this one a little bit. Now I'm going to increase the surface area by using a red pen. So the reaction will be steeper. Wow, I overshot. The reaction will be steeper, but it has to finish at the same point. So has to finish at the same point. I mean the same height. The reaction obviously leveled off earlier because it was quick. So all these have time on the x-axis, let's say, and let's put volume on the y-axis. Now for the next one, you have to be careful. So before I do the temperature one is easier. If you increase the temperature, there's a higher kinetic energy, particles move faster, and the FOSC increases. So once again, you start off steeper, level off earlier, and level off at the same point. So this will be T2, this will be T1, and T2 will be bigger than T1. For this one, we have a higher concentration here. And the black line is the lower concentration. That's not concentration, sorry, surface area. The concentration is the last scenario we need to know how to draw for. Now this one you've got to be careful because it depends which one's in excess. So if we're collecting volume of gas and the marble chips are in excess, then if we double the concentration, then we should be able to produce twice as much product and faster. So we have to draw it steeper at double the height. So this is double the concentration. If marble chips in excess, because the acid was what was limiting the reaction. So if you double the acid concentration, you're no longer limiting the reaction. So you roughly double this distance. However, if the acid was in excess, then the marble chips are limiting the reaction. So even if you add more acid concentration, you cannot produce more product, but you can make it faster. So then it would look the same as the other ones. So this one here would be, if there's a higher concentration of acid, but the acid is in excess. All these reactions are for calcium carbonate. Plus hydrochloric acid. That's all these reactions. So they're making CO2 gas. So if we save this, and now I'm just going to go through one exercise where different things are going to change and we're going to sketch it. Be a little bit messy, but you just have to pay close attention. So with this newfound knowledge, this will be the task. So this is our task. We have CO2 being produced with marble chips and acid reacting, and the marble chips, importantly, is the one in excess. So the acid is limiting the reaction. So let's have a look at this table and use different colors for these things. Let's start with the first one is for reaction 1 is being done, is the black curve. So reaction 2, let's see what changes. So if reaction 1 has small and this one has large, think which one has the higher surface area since everything else is the same. Well, large chips would have a lower surface area. The small ones would have a higher. So the rate will be lower. Okay, so this will be number 2. Change color to blue. The next one is going to be smaller and small, so it's the same as the first one. 2, 20, but the volume of HCl has been doubled. If you double the volume, you will double the amount of product you can form, because as we said, the HCl was limiting since the carbonate was in excess. So that would actually mean that you would have to draw it finishing at double the height. 1 second. I do have all this, by the way, explained here. Okay, so I'll post that as well for you. Now, if we go back to this, that's a different lesson. Going back to this now. The concentration will actually stay the same, funnily enough, because the concentration is still 2. So if you did 2 per 100 or 2 per 200, you've increased the volume of acid there. So the volume of acid has increased, but not the concentration. So I'm going to draw it similar to the first one, but double the height. So I'm going to call that 3. Then I'll try and go to a darker blue. Small, 100, 100, 20, 20, 2, 4. You've doubled the concentration. So if you double the concentration, it will be twice as fast. Okay, so this curve has to be twice as fast. And now the question is, where do you finish it? Because obviously in an exam, they mark you on 2 marks, 2 points. Where does it finish? And how steep is the gradient? So you can use a little trick from the moles lesson. If you do moles equals concentration times volume, then you can see the volume is 100. So 2 times 100 will be 200, obviously divided by 1,000. But we don't need to worry about that. So 200 compared to, in questions 3 and 4, is going to be 400 and 400. So that's twice as much moles, which would imply finishing at twice the height. The only catch here is that nobody mentioned the water. That's why I'm a little bit paused. So actually, because the HCl is still only 100, even though the concentration is greater, that would simply mean that the water was lowered in order to achieve that effect. So I'm actually going to finish at the same height, but make it steeper. Okay, bit of a messy, but that'll be my number 4. So that was a very unique situation because the concentration was doubled, so naturally it should finish at twice the height, but it was doubled in a weird way. It was doubled without actually doubling the HCl. They must have halved the water. So this is actually correct. And it is explained in my explanations. Right, number 5, small, 2, 2, 100, 100, 20, 30. Nice and easy. Temperature was increased, so the reaction should just be faster. So it was going to be like this. Now remember, it's getting a little bit messy, but there's no way to compare 5 and 4. You just need to make it steeper than the first one, which is number 1, the black one. Okay, then we go to 6. Small, and catalyst. That's the only change. 2, 2, 100, 100, 20, 20. Catalyst would be faster and finish at the same point. I'm running out of space, and I'm going to go for a dark green, and I'm just going to go like this, because it should finish again the same, but be faster. Again, it doesn't matter which of these are faster out of 6, 5, and 4. It just has to be faster than the black line. And number 7, small, 2, 1, concentration was halved. Volume of HCl though was doubled. Temperature the same. So this is another one that's interesting. They've halved the concentration, but they've doubled the amount of HCl. So in this one, we have twice the volume of HCl, but half the concentration. So it must go slower. And it will only achieve, so it should go slower than the black line. Let's go for a black pen, purple pen if you want. So the question is, where do you finish it? Well, I'm going to make it finish at the same point still. That'll be my number 7. Okay, because they do have half the volume, they do have double the volume, but half the concentration. So it just be slower, but finish at the same point. Okay, that completes my curves. Remember, the black one is curve 1. A bit messy, but this is quite a high level question. You normally only get changes in concentration or temperature. You don't get changes in both of these. So this was very high grade stuff to challenge you. Okay, that's the end of the curves lesson. There's one more lesson on practicals and independent, dependent variables. So see you then.